Hello everyone, and welcome to the third and last session of this intermediate three-part ARSET training titled Solar-Induced Fluorescence Observations for Assessing Vegetation Changes Related to Floods, Drought, and Fire Impacts. I'm Dr. Erica Podest, a scientist at NASA's Jet Propulsion Laboratory, and I'm also an instructor with the ARSET program. Today's session will be focused on how to work with gap-filled SIF products, and it will consist of a theoretical session and a demonstration. Our invited expert is, once again, Jackie Ryan from NASA's Jet Propulsion Laboratory. So today is the last session of this three-part training, and it's focused on how to work with gap-filled SIF products. There is a homework associated with this training, and it is open as of today. You can access it through the training website. The due date is November 12, and we will be providing a certificate of completion to all of those participants who attended the live sessions, all three of the live sessions, and complete the homework by the due date. The certificate of completion will be received, or you can expect to receive it in about 3 months. And this is a reminder of the prerequisites for this training, which is the fundamentals of remote sensing, as well as a SIF ARSET training that we did a couple of years ago. It was a combined SIF and LiDAR, so the prerequisite here is for you to review the SIF portion of that training. And here are the trainers for this session. I'm the ARSET training coordinator for this webinar series, and we have an invited expert. Once again, returning is Jackie Ryan. She is a data visualization developer at NASA's Jet Propulsion Laboratory, and she will provide a discussion about the gap-filled products, and then she will do a demo to show you how to access and visualize these products. How to ask questions. Please write your questions in the questions box, which is located in the bottom right. There are 3 points. There's a menu that will pop up. Select the first option, which is Q&A, and there you can write your question. Feel free to enter your questions during the presentation, and we will try to respond all of the questions during the Q&A session after this presentation. The remainder of the questions, if we don't get to answer all of the questions, we will answer them in the Q&A document. So we compile all of the questions into a Q&A document, and we will post that document on the training webpage in about a week. So let's get started with session 3, working with gap-filled SIF products. Our invited expert is once again Jackie Ryan from NASA's Jet Propulsion Laboratory. She'll be presenting the rest of this session, so cover both the theoretical portion and a demonstration. Welcome once again, Jackie. Great to have you back.
Hello and welcome to the third part of this ARSET course on solar-induced chlorophyll fluorescence. In this exercise, we'll be discussing the use of gap-filled SIF products for vegetation analysis, using the GoSIF dataset created by a team out of the University of New Hampshire as an example. In particular, we'll investigate a case study involving the 2019 Midwestern floods and their impact on agriculture in the Corn Belt. Here's a brief overview of what we're going to go over today and the main objectives for what we hope you'll get out of the Jupyter Notebook code demonstration. Before we dive into the code, though, I'd like to provide you all with some context on SIF measurements collected by other spacecraft. Thus far, we've been using OCO2 and OCO3 exclusively in our exercises as a matter of course, without really discussing data sources from other missions. The OCO missions are not unique in collecting SIF. So depending on the needs of your own analysis, you might find it useful to incorporate data from other sources. In fact, the primary point of our discussion today is to highlight some of the limitations of exclusively relying on the OCO2 and OCO3 observations that we've used in the first 2 parts. By using a gap-filled product, we can obtain a broader spatial context for the impact of the flooding event in our case study. And you can see a satellite comparison view in the image on this slide. So the left side is 2018 and the right side is 2019. The floods that year in 2019 were extremely severe and caused the loss of 3 lives as well as significant damage to property across about a dozen states. In the notebook, we'll just be focusing on the impacts to terrestrial plants rather than any of the economic or social impacts. And in specific, we'll be focusing mostly on cropland. The basis for this analysis comes from the Yin et al. 2020 paper, and we'll be discussing their results a little later. Finally, as an extra point of comparison, we'll look at a bonus case study examining the impacts of the 2012 Midwestern drought on cropland in the Corn Belt. Before we dive into discussing other sources of SIF data, I want to review why we're even using SIF for vegetation analysis in the first place. If you're familiar with working with multispectral remote sensing data for this type of work, then you might be aware that there are numerous types of vegetation indices that can be produced from satellite data. Some examples of these are the Normalized Difference Vegetation Index, NDVI, the Enhanced Vegetation Index, EVI, Near Infrared Reflectance from Vegetation, or NIRV, and the Chlorophyll Carotenoid Index, or CCI. All of these indices are produced by taking a ratio of observed spectral signals as a heuristic for photosynthesis, or at least for measuring the vegetation health in the environment. But the most direct measurement we're actually interested in is gross primary production, GPP, which is a measure of carbon fixation performed by an ecosystem. While GPP is the best possible measurement we could look at in vegetation analysis, at least from a remote sensing perspective, it's very challenging to observe from space. As an aside, there are some SAR-based measurements that can measure biomass, like the recently launched ESA spacecraft, itself called Biomass, but this approach is relatively new and data coverage is limited. With all that being said then, because of the challenges of using GPP directly, it is often necessary for us to use alternative measurements. The plot on this slide compares some of the metrics I've mentioned against GPP to show how well they're correlated. This data is for boreal forest in northern Canada, so the correlation will vary somewhat depending on the biome type used in your own analysis or in the case study we'll look at today. For example, in this case, CCI is almost as correlated with GPP as SIF is, but CCI is particularly well suited to studies of gymnosperm-dominated biomes like this boreal forest due to the phenological changes and reflectance in the needles of evergreen trees. In other words, in the deciduous forest, evergreen broadleaf forest, or in cropland, we might not expect to see the same correlation between CCI and GPP. So I want to take a moment to look a little more deeply at this plot. Starting at the top, we can see that SIF is the best correlated variable with GPP with an R-squared value of 0.92. The second best, as I mentioned, is CCI with an R-squared of 0.9. However, I also want to take a moment to point out NDVI with its R-squared value of 0.79. You may already be familiar with NDVI from your own research or analysis, since it's easy to measure and therefore it's commonly used across a wide variety of applications. In the case of our boreal forest here, even though it has good overall agreement with GPP, it does exhibit a hysteresis effect during winter. In other words, GPP tails off down to 0 in late October or early November, but NDVI remains high into December. Since NDVI is mainly measuring a plant's coloration, it will tend to be a lagging indicator of vegetation health. Short-term stresses, like those caused by floods, drought, or extreme heat, might not show up in NDVI until a couple weeks after photosynthesis has stopped. SIF, on the other hand, is more dynamic, meaning we're more likely to see rises and falls in activity in response to stresses, even within a single day. If you recall Nick's explanation in part 1, this is because SIF signal is tied to the photochemical quenching reaction, which in turn tells us how open the photosystem reaction centers are within plants across an ecosystem. So hopefully you're convinced now that SIF is an excellent metric for studying vegetation health and stress response. SIF is a relatively new type of measurement for spacecraft, with GOM-2 on MEDOP-A back in 2006 being the earliest instrument capable of picking up the spectral signal directly. This wasn't an original use case for GOM, and the dataset itself was derived later. The first dedicated SIF datasets from space-based remote sensing were actually developed in 2011 by Joanna Joyner, Luis Guanter, Christian Frankenberg, and others using JAXA's GOSAT satellite. OCO2 followed in 2014 and improved upon the existing SIF record. More recently, we now have TROPOMI on board ESA's Sentinel-5P spacecraft, which launched in 2018, GOSAT-2 launching in 2018 as well, OCO3, which launched in 2019, as we've previously discussed, and most recently, the Chinese Academy of Space Technology's GOMANG satellite, which launched in 2022. All of these satellites have publicly available data, with the exception of GOMANG, and sometimes your analysis may be improved by combining or regridding data from multiple satellites into a single product. So it's useful to keep these in mind to know all the tools you have available when looking at SIF. So the first other satellite that I want to talk about is GOSAT. As I mentioned, it's been around the longest of all the data sets, but it suffers from low data availability in a spatial sense. As you can see from the plot here, which I've taken from the Doty et al. Paper that we looked at in part 1. So GOSAT here is up at the top, and then we see gridded rasters of OCO2 and OCO3, very similar to the plots that we created in part 1. Like many other Earth-observing satellites, such as OCO2, GOSAT has a sun-synchronous orbit. So it will see a point at a given latitude at the same solar time every single orbit. While GOSAT improved upon the resolution of GOM, it's still only about 0.1 degrees, so it's best used for ecosystem level analysis. That might be difficult to tell from the figure on this slide, because the OCO data has been gridded to a resolution of 0.5 degrees alongside the GOSAT data in this case. You can find more information on the data from the 2 papers that I've linked the DOIs for. And you can also find the data itself in the dataset link that I've included on this slide. TropoSIF is another great resource to use in addition to OCO2 and 3 data. Most of the research papers that we've referenced in this course make use of TROPOMI data to augment other sources of SIF, and for good reason. As you can see from the plot on this slide, the spatial coverage is quite substantial, and retrievals are available at a sub-daily cadence. Although we aren't covering its usage in this course, you're encouraged to take a look at the TropoSIF dataset on your own. One thing to note is that there's no direct comparison between OCO2 and 3 757 nanometer SIF and the SIF from TROPOMI, so it's best for you to compare only the 740 nanometer SIF data between the 2 instruments. And again, as with GOSAT, I've linked a paper describing the theoretical basis for the SIF retrievals from TROPOMI, as well as a DOI link to the dataset itself. Let's turn back now to the OCO3 gridded raster plot that we made in the first notebook exercise. When you look at this plot, you can tell that for June 2020, and in general for any given month, there's relatively limited spatial coverage. Although the ISS orbits every 90 or so minutes, the low swath width of the instrument means that there's going to be gaps in coverage for some months. Additionally, because of the inclination of the ISS's orbit, there's a seasonal bias as to which areas get more daytime coverage during certain times of year. For the CONUS, this means that we get a lot of coverage during May and June. You may have noticed this when looking at what dates SAM observations are available for during the second exercise. Another challenge that we encounter with any of the products that I've just mentioned is that their observational record only goes back about a decade. For OCO2, we have 11 years of data, and at the most, there's GOM, which stretches back to 2007, but even that is not very long. For OCO3, we have just 6 years of data, and even then, instrument anomalies and time spent powered off means that there are significant gaps where no data was being acquired. With all of these limitations in data availability for spacecraft observations, it begs the question, can we do better? Is there a technique that we could use to improve the coverage of this data and estimate values that we have not observed directly using indirect measurements from other satellites? And as you may have guessed already, the answer is that we can use a technique called gap filling or data fusion. There are many approaches to doing this, but the basic premise is that we need to train a model using a data-driven approach to predict the value of a measurement, in our case, SIF. The value we are predicting is called the label data, and the ancillary measurements we use to aid in predicting the value are called predictor variables. These can include land cover classification, surface reflectance, or meteorological data like vapor pressure deficit, VPD, air temperature, and downwelling shortwave radiation, or DSR. That last one, DSR, is similar to photosynthetically active radiation, or PAR, and that it quantifies how much solar energy a plant can receive at a given time. So for an example of how we could do gap filling, we could take MODIS data, which has a resolution of up to 500 meters per pixel, and gives us all of the predictor variables that we need. And we can associate those predictors with the observed OCO2 or OCO3 data and use all of that to train a model. The model can then tell us what we expect SIF to be in places where we have no direct observations. The modeling technique that you use for this gap filling is a matter of debate in research, but the product we will be using in this exercise is based on a QBIS regression tree, which is a data-driven approach rather than machine learning. With that being said, there are definitely teams using machine learning to do gap filling with SIF data, such as the works discussed in Junjie's presentation in part 2. Now let's talk about GoSIF, the dataset that will be the star of the show for our code demonstration today. GoSIF was originally developed by Xing Li and Jingfeng Xiao at the University of New Hampshire in 2019 by fusing OCO2 data with MODIS. What they ended up with is a spatially contiguous global product at 0.05 degree resolution, or about 6 kilometers per pixel, and 8th day temporal resolution, although there are also monthly and annual products. The reason we can only get 8-day resolution out of the data is because MODIS is only able to produce a BRDF, or bidirectional reflectance distribution function, every 8 days. And that's a required ingredient for determining the surface reflectance. Reflectance for this purpose requires taking many observations of the atmosphere with and without clouds. And so, as you might imagine, that can require several days of observations on average. Remember how I mentioned that the observational record of OCO2 only goes back to 2014? An advantage of using MODIS for this purpose is that we can now estimate SIF all the way back to when Terra and Aqua were first launched in 2000 because of the observational record of MODIS. If you'd like to read more about the derivation of GoSIF, you can find the paper in the DOI on this slide. I've also included a direct link to the data store on the UNH website, although we'll go into detail about downloading the products in the code demonstration. For this next slide, I want to talk briefly about some other gap-filled products, and Junjie has already gone over this research, so I'll only touch on it briefly here. But there are other products that you can consider using in your own analysis. None of these have the easy data availability that you would get with GoSIF, though, so you may need to reproduce their technique rather than going to a website and downloading data. Xiaoying Zhang and her team developed a diurnal SIF product 0.5 degree resolution using climate model data for predictor variables. If you recall, I mentioned that OCO3 will observe the same location at different times of day due to its orbit, and this makes it a great resource for developing diurnal models, or models that can predict SIF at hourly cadence throughout the day. This can be used to demonstrate plants' response to heat stress in the afternoon. In many places where it gets really hot, like tropical rainforests, the plants will largely close up their leaves to preserve water and engage in non-photochemical quenching, in other words, heat production, to avoid drying out despite having plenty of sunlight. This can be observed as an afternoon depression or drop in SIF values. The figure I've included on this slide shows that behavior in action. And you can see that in the final time bin for a given day over the Amazon rainforest, as the researchers pointed out in this study, there's a noticeable drop in SIF, about equal to what's seen in the morning, and an increase in water use efficiency. Another product to look at is called EcoOCO3. The OCO3 science team is currently working on a product that combines ecostress land surface temperature data with OCO3 SAM mode measurements as a means to quantify water use efficiency. And water use efficiency, as was mentioned in this other study as well, is a measure of how efficiently an ecosystem uses water to fix carbon. So this figure shows an example of an EcoOCO product. This is not a gap-filled product per se, but it's another example of data fusion in action. Lastly, GeoSIF, which was also covered by Junjie, is a gap-filled product produced by combining the Korean GK2A weather satellite for predictor variables to provide hourly data for estimating SIF in East Asia. All right, so now we want to dive into our case study for today and consider how the researchers did their own vegetation analysis. The scientists, of course, used SIF to investigate impacts, but they also considered terrestrial water storage, TWS, from the GRACE follow-on mission, atmospheric CO2 concentrations from the ACT America Airborne campaign, as well as from OCO2 itself, and GPP data derived from those measurements. The reason for using CO2 concentrations in this context is that it's another way to gain insight into GPP behavior. Since if CO2 is elevated over a region of cropland compared to normal, then it indicates that plants are fixing less carbon than we would expect. Unfortunately, there were thick clouds over most of the Corn Belt during this period, which somewhat limited the data availability during June and July, but the paper was still able to demonstrate early season growing conditions over cropland exhibited much lower than normal GPP, as can be seen in the second plot on this slide. This can also partly be explained by delay in planting, which is why we see an uptick in GPP later in the season. In fact, the crops were able to take advantage of the additional water in the soil later in the season. In the top plot of this slide, you can see that TWS was 2 standard deviations above the mean in the flood year. Interestingly, we can also notice from the middle plot that non-cropland areas were less affected by the flooding. Natural biomes are usually better adapted to periodic flooding due to the existing trees and root structures that help hold the soil in place. So let's turn over now to the SIF analysis that the researchers did in their study. In their case, they used Tropomi SIF at 740 nanometers, spatially aggregated to a county level, and took the difference between 2019 and 2018 for each month over the growing season. Reinforcing the findings that we looked at in the previous slide, you can see that the delayed planting date in this last plot over here, up to 5 weeks in the case of Illinois, meant that the early growing season exhibited much lower than normal SIF. So if we look at the June data, we can see that the difference over here shows lower than normal SIF. On the other hand, the late season had higher than average SIF over here. One question to ask is, do you expect to see similar results in the GOSIF data between 2018 and 2019? This might seem obvious, but my hope is that it will build your confidence about using gap-filled products in this context. Another question to keep in mind is, do you think that the later peak balanced out the earlier dip in primary production? In other words, what might the overall effect on yield be in this particular year? And to answer that last question, we can just pull up agriculture statistics curated by the USDA and see that corn yields in the US in 2019 were about 5% lower than in 2018. When we're looking at this data, how is the SIF correlated with crop yields? As Junjie showed in her presentation, the most thorough way of comparing the two is by incorporating climatology to build a rigorous estimate. In an oversimplified sense, though, we can consider that the total yield is tied to integrating under the curve of SIF or GPP. In other words, by summing up the values that we see in those metrics throughout the season. This mainly works for annuals because the harvested crop completes its entire life cycle within a single season, as opposed to perennial crops whose yield can be impacted by previous seasons. Looking at this yield chart, you'll also notice there's a conspicuous dip in corn yields in 2012. This motivates our bonus case study where we'll be looking at the impacts of drought on crop production in that year. 2012 was a severely hot and dry year in the Corn Belt, and there was no extra water storage to mitigate the effects like there was in 2019. By comparing 2012 and 2013, we can see that there was a 22% drop in yield between the years. This is made slightly worse by the fact that there's an upward slope to the yield graph due to improvements in agricultural practices, crop protection, and better hybrids that get released year over year. So that is the upward trend line that I'm referring to here. That concludes the presentation portion of this part. And now let's turn over to the code demonstration. Now that I've explained the context of what GoSIF is and why it's useful for our analysis, I'd like to turn over now to the code demonstration. Today we'll be looking at the third notebook, gosif.ipynb. And as in the previous exercises, you'll first want to load up the Jupyter Hub environment using the setup script I provided. So I'll jump out of this presentation now, and you can see I already have a terminal window open. So I'll be using this terminal window to open up my Jupyter environment as we did with the previous examples. First, I'll want to navigate over to where I have the code. This may be different depending on where you cloned the repository on your own computer. And then, as before, I'll run the setup script. Since I'm on a Mac, I'll use setup.sh. If you're on Windows, you'll want to run the setup.ps1 PowerShell script. Okay. And I see that now my server is running. And I'll pull down my browser window so that you can view the Jupyter environment that I have open. I'll now want to navigate over to the third notebook. I'm just closing the other tab so that we can focus on the task that we're going to be discussing today. So you should now see working with GoSIF data in your Jupyter environment on your screen. The first cell here that we're going to be running is just importing libraries as we've done in the previous exercises. So I'll run that cell now. Okay, with that out of the way, the first portion of the exercise is just going to focus on downloading GoSIF data itself. And to reiterate what was discussed during the presentation, this data set was produced by Dr. Jingfeng Shao and Xing Li at University of New Hampshire. And they took OCO2 data and produced a model that's able to estimate it at 0.05 degree spatial resolution, or about 6 kilometers per pixel, on an 8-day, monthly, or annual cadence. And they used a number of other predictors to estimate these values in a gap-filled manner. And this is the gap-filled product that we were talking about from before. I've already written a helper function called download and unpack GoSIF, which will make it easy for us to download data from the UNH data store. Before we go ahead and download the data, though, I want to pull up that site so that you can see where this is coming from. So here's the UNH website containing the GoSIF dataset. And this is the cover page for it. And if I scroll down here, you can see down at the bottom of this web page, it says download GoSIF. And if we click on that link, that will take us to a data store like this. You can see that there's 3 different time cadences for our data. If I click on 8-day, you're able to see a number of TIFF files that have been packed using gzip. And these TIFF files have dates associated with them. There's a year and a day of year. And these estimates go from the year 2000 all the way through to the end of 2024. So there's a wealth of information here for us to work with. You can see that each individual file is about 10 megabytes. Okay, so let's return now to the notebook. The example file that I've selected for us to work with is from June of 2020. And as we've been doing in other exercises, I'm going to store it in the data directory within our notebook environment. We're going to create a new directory called GoSIF for storing this data. If you provide a day of year, you will get the 8-day data. Since I'm providing a year and a month, the function will know that I'm asking for monthly data. And if I provide only a year, the function will download the annual file from the data store. Okay, so you can see that our progress bar shows that we just downloaded the file. It was 9.3 megabytes. And it unpacked the gzip to turn it into a geotiff file. If I go into my data directory, you can see that there was a new GoSIF directory that was just created, and we have our TIFF file right here. Now, the default Jupyter Notebook environment will not be able to view this geotiff file. Some operating systems can handle this natively, but generally speaking, geotiff is a format that's intended for GIS software, and it's not always the easiest to work with. If I turn over to my Finder window, which I have over here, and I look in my data directory, and I see my new GoSIF directory right here, I can take a look at this geotiff that we just downloaded. Now, this doesn't look like very much right now. You'd see a lot of gray areas where we have no data. You can see white areas where there's desert region and no SIF activity. And then we see a whole bunch of black. And actually, this is varying shades of gray associated with the SIF value in the particular area. But it's very difficult for us to understand what we're looking at when we just look at the raw version of this geotiff. Because of that, for the purposes of visualization, I've added additional functions that will convert this geotiff to a PNG. So let's take a look at that code cell that does the conversion to PNG. There are a few values here that are sort of like magic numbers, which actually come from the user's guide for the data. If I turn back over here to our data store web page that I showed you earlier, you can see there's an included PDF over here. And if I open that up, which will take a moment to load, you can see that the authors of the dataset have included some helpful information for understanding what we're looking at with the data. For one thing, our units are watts per meter squared per micrometer steradian. which is the same unit that we've been using for SIF throughout these exercises. However, the scale factor is 1 times 10 to the minus fourth, which means that this is a value that we have to multiply the raw values from the geotiff by to get the values in the proper unit over here. Additionally, there are 2 fill values, which are associated with data where we would not expect to find SIF activity in these files. So we'll need to filter out those values and treat them as a transparency when doing our conversion to PNG. Okay, so turning back over to the code, you can see that we're accounting for our 2 no data values with this data threshold right here. So we're only going to use any value from the geotiff with a number less than 32,765. After we filter the values, we'll be scaling by the scale factor that's been provided. And that should give us a result that is in the watts per meter squared steradian micrometer unit that we expect. Okay, so I'll run this cell. So now that we've run the cell, we've converted our geotiff file that we downloaded from the UNH data store into a PNG with associated metadata in a JSON file. If you're not familiar with the geotiff format, it contains georeferencing information embedded in the file itself. Because the PNG format does not support georeferencing information natively, we've included it in an ancillary JSON file for use later in our visualizations. Let's take a look at the files that we just generated to see what they look like. So I'll turn back over to my Finder window, and I'll open up this PNG map. So you can see that this is a significant improvement in being able to view the data intuitively compared to what we were seeing with the geotiff. You could also accomplish this by viewing the information in a GIS program like QGIS, but since we're in a Jupyter notebook, I thought it would be helpful to include these PNGs. Now, one thing you may have noticed is that there's no scale reference for the SIF values in the PNG. There is one other parameter that I haven't mentioned yet, which is our Vmax parameter, similar to the Vmax that we used in other exercises throughout this course. In this case, Vmax is scaled prior to the scale factor being applied. So a value of 8,000 here corresponds with 0.8 watts per meter squared steradian micrometer. And this is about in line with the SIF values that we were seeing for June when creating our gridded raster. One thing to note about the GoSIF product is that its values are based off of the 757 nanometer SIF from OCO2. So the scale of SIF values that you would expect to see should match with true observations at 757 nanometers, rather than the 740 nanometers, which are common for peak SIF values. All right, with our data preparation out of the way, we can get to the fun part, which is actually looking at our data on a map. I've written a helpful web-based widget for doing that, and you can see that the setup for it is in this cell. What we'll be doing here is running the widget, which is actually a web page that will run locally on your computer that enables us to look interactively at this file. One thing you might have noticed when we pulled up the PNG is that there's really a lot of information in these files, so it's helpful to be able to zoom and pan around to really get a sense of every detail of the data. Let me run this cell now. And if I scroll back up, you can see that a map has opened within our Jupyter notebook. If you find that the aspect ratio of this makes it a little difficult to view the information itself, there's also a link here, and this will open the map in a new tab. So with that open, we should now be able to look at the converted SIF data from the GeoTIFF in more detail. And you can see I can zoom when using the scroll wheel or when using the plus and minus buttons over here. And if I zoom in on the United States, you can see this particularly active area in the temperate forests of the eastern United States. So over here, one of the details we can see is that this area of relatively lower SIF is the US Corn Belt. And in June, typically that's right at the beginning of the planting and growing season. So the crops have not actually reached a mature enough stage to have a significant SIF signal yet. On the other hand, the broadleaf forests of the eastern United States show a significant amount of activity in this late spring, early summer time of year. Let's see what other details we can see around the world in our SIF data. One of the incredible things about this GoSIF data is that because we've done gap filling now through the GoSIF technique, we're able to actually view any part of the world for any time step that has data available. Whereas when we were producing gridded rasters, we still ended up with gaps in the data due to areas that the orbit of the ISS or OCO2 did not cover during the time period that we aggregated over. One thing we can see in mid-latitudes near the equator are the two tropical rainforests of South America and Africa. And these areas show moderate levels of SIF, lower than the temperate forests of the Northern Hemisphere at the same time of year. And that's consistent with the year-round photosynthesis that we see in the rainforest regions of the world. On the other hand, in desert regions, such as the Sahara Desert, the Mojave Desert in the western United States, and the deserts in Chile and Argentina have quite low values of SIF, which is associated with lower plant activity in those regions. One last detail I'll note here is that because of the thresholding that we did, we were actually able to filter out ice and water values, which have no SIF activity, and would just cover over important context in our map. And that was the point of the thresholding step that we did earlier. The last thing I'll point out on this widget is that the folder icon up here enables you to open other converted GoSIF granules that you may produce throughout this exercise or in the homework exercise. And this is really handy if you want to view other data later. You don't have to rerun the cell or perform any additional code steps to visualize it. Now, the details for actually implementing something like this widget that we're using here are rather complicated, and it's not terribly relevant to the discussion of the data itself. So I'll leave it out of this demonstration. It's not necessary to create an interactive plot or anything this complex for viewing GeoTIFF data. This widget was merely meant to take the place of loading data into GIS software like QGIS, which is what you normally might do when evaluating a new data set like this. Before we continue to the case study analysis portion of the exercise, I want to return to the previous cell and show you one more feature that we can use when analyzing these granules. I'll scroll back up to the previous cell. When we ran this cell originally, you may have noticed this commented out line. Similar to when we were creating gridded rasters in part 1, we can add an argument that bounds the data to a specific georegion. In this case, the commented out arguments allow you to bound the data to the CONUS. So I'll uncomment this line, and if we rerun the data, we have converted the file again. And looking in Finder, you can now see that our converted GeoTIFF only contains data over the CONUS. This can be useful when speeding up our processing later on in the analysis. If I return to the map and I rerun the cell, now you can see that the data has automatically been zoomed in to the United States. And let me turn back over here and refresh the page. And when we open a file that has a bounded georegion, it will automatically zoom the view to that georegion that you've selected. This is handy for automatically setting up where you want to see the data instead of having to pan around and find it yourself. I will note, however, that I didn't change the file in this case, so if you are generating many PNGs in this manner, you might want to specify a new output file name so you don't overwrite previous data. And if I go back up to the previous cell, you can see that the file name is contained in the GOSIF PNG variable here. And we've specified it here to be the same as the GeoTIFF's file name, but with the PNG extension. So if you wanted to change it, you might add something here like _ CONUS. All right. So I'll remove that for now. Another side note before we continue on is that the researchers also created a data set estimating GPP from GOSIF data using the linear relationship between the two quantities. Remember how in part 2 we showed the linear relationship between SIF and GPP in ideal conditions? If we go back to Dr. Xiao's website, and let me go back here, and we scroll back up on this page, you can see a GOSIF GPP webpage on the sidebar here. You click that link. This is the cover page for that data set. And here's some information on the validation of the relationship between the GOSIF GPP product and Tower GPP, showing that the results achieved by the researchers agree quite well with ground-based measurements. So this can be another useful resource when performing vegetation analysis, although we won't cover it directly in this course. However, if on your own you'd like to look at that data yourself, you can do so by adding in the keyword dataset equal to GOSIF GPP _ v2, like so. And now when you download the data, it will actually use the GPP data from the UNH data store. One thing to note, though, is that the scale value and threshold values are a little bit different for that data set, so you'll need to tweak some of the other parameters yourself to get it to work. Again, we won't be covering that in this course. I just wanted to note it down if you did want to look at the GPP data on your own. With that side note out of the way, now we're going to use this product to perform our own vegetation analysis in the spirit of the Yin et al. Paper that I talked about in the presentation. To recap, we'll be looking at how the 2019 Midwest floods affected agriculture, especially the corn and soy crops that make up a majority of the cultivated land area in this region. This event was a big deal. It was the wettest January through August period in over 125 years. There were fields that were underwater, farmers couldn't plant their crops on time, and the crops that did get planted often drowned. The first thing we'll need to do to understand the scale of this event is to download all of the granules over the entire growing season. And we'll use the 8-day product here instead of the monthly that we used in the first section to have the best temporal resolution for our analysis. You can see the instructions here in the explainer text that I've included. So we're going to download 8-day average GOSIF from March through October of 2018, which will function as our control year, and 2019. And 2019, as a reminder, is the flood year. In step 2, we'll use the conversion function that we used before to get all of the data to use the same skull. In step 2, we'll use the conversion function that we used in part 1 to convert all of the data to the same color scale from 0 to 0.8 watts per meter squared steradian micrometer so that the data can be compared visually. We'll also perform the bounding operation that I showed you to make the data only appear for the US Midwest, which is our region of interest. We'll compile the map data into an animation, which is a helpful way of visualizing this and getting an intuitive qualitative understanding of the event. Lastly, for a more quantitative approach, we'll be creating a time series to see the year-over-year difference in SIF within the region of interest. Okay, so let's take a look at our first cell here. That's going to be performing step 1 as before, which is just downloading the data. And the date range that I've included is from day of year 73 to day of year 298. These 2 dates weren't chosen for any particular reason other than that they cover the growing season with a little extra. And here you can see our function working. This will take a couple minutes. Okay, so now our code cell has completed and we've downloaded all of the data over the growing season for 2018 and 2019. Before we continue with the analysis, I want to mention that although looking at SIF is not comprehensive, if you feel confident about this material so far, you can also incorporate the estimated GOSIF GPP product that I mentioned and the XCO2 product from the OCO2 and OCO3 missions, similar to the SIF product if you've been following along from part 1. This would represent a more comprehensive analysis in line with the study. If we turn over to the study, I can show you a little more detail on what I mean by that. I touched on this in the presentation, but I'll show you the study directly now. In particular, I want to point out this plot, which not only compared SIF from Tropomi and OCO2, but also considered the planted area to show the delay in crop planting in 2019 and the delay in the peak in SIF. One more detail to look at is the terrestrial water storage, which I also touched on. That comes from GRACE follow-on data, which I won't be covering, and the GPP data. Now, this GPP can be reproduced by downloading the GPP data from GOSIF, and you can see how well the results match or maybe don't match what was found in the study. Additionally, the researchers considered XCO2. If growth is less in a region, then XCO2 would be higher in general, and that is due to less carbon fixation from the plants over that region. So that's another reason to consider XCO2 when performing this type of vegetation analysis. let's return to the notebook. With our SIF files downloaded, we now need to convert them to produce the animation. I've created a function called create GoSIF comparison animation here, which will take the files that we just downloaded, perform the conversion function, and create an animated GIF file that actually shows the animation itself. So let's run that now. This was not actually part of the study itself, but I find it instructive to animate the data over time in a side-by-side graphic. Okay, so now the cell has run and our animation is displaying down here. I'm going to wait for it to loop back around. While you could look at the granules individually in the map widget that I showed you before, it's easier to compare them in this animated view, in my opinion. So let's take a look at what's happening right now. You can see that SIF is peaking over here on the left in 2018, while it remains relatively muted over here on the right. Subsequently, later in the growing season, SIF reaches a somewhat lower peak in August and September, whereas SIF is relatively low over on the left in our control year. You can play through this animation multiple times if you missed it the first time. You might notice new things each time that it plays through. While this is useful for getting a rough qualitative sense of the scale of the event, it's helpful for us to also include a quantitative analysis using a time series to actually see the difference in peak over time in this region. Another thing that you'll note about this graphic is that there's a red polygon over the Midwest. And this polygon identifies the rough shape of the Corn Belt region. I didn't use any specific heuristics for creating this polygon. It was just based on an interpretation of where cornfields roughly lie in the US Midwest. So it's not comprehensive. In general, you might include aggregating all SIF data within a given state. However, that might include some wild regions within your analysis. An alternative would be to use something like the USDA's cropland coverage product to specifically filter to data that is only cropland. But that is a little bit more complicated than what we'll be doing in this analysis. So for creating our time series, we'll actually be averaging all of the SIF values within this polygon. And the percentage of planted regions within this polygon is quite high, so we should mostly be seeing a cropland signal. If you're curious about the data points or the spatial points in this polygon itself, that is in the cornbelt.geojson ancillary file over here. So I want to point out one last thing before moving on from this animation and looking at our quantitative analysis. Let's take a look at this region down here in Missouri and a little bit of Arkansas below the red polygon. This corresponds to the Ozarks region, which is mostly deciduous broadleaf forest. And unlike planted cropland, the wild regions like this experienced a lower impact on SIF and actually had a slight uptick in SIF activity during the flood year. This area was more resilient due to the established root structures and the selection pressure on species to be more adapted to flooding. For instance, in floodplains of rivers, you might see plants like cattails, which are more resilient to flooding, as I said. In the Yin et al. Paper, the researchers noted an increase in productivity of 0.04 petagrams of carbon in 2019 compared to 2018 across all land types in the 17 states included in the study. So the effect of wildland regions on the overall average across all 17 states actually resulted in a slight increase in primary productivity. On the other hand, the cropland regions experienced a 0.21 petagram of carbon drop in productivity in June and July in the flood year, with a corresponding increase of 0.14 petagrams of carbon in August and September due to the later peak. Remember, we saw that peak in August and September in our animation where that dropped over here. So just doing the simple math, that resulted in a net loss of 0.07 petagrams of carbon overall in the flood year over cropland regions specifically. Let's see if we can see that same trend in the quantitative analysis. So let's take a look at the cell that we have down here. Again, we're using the cornbelt.geojson ancillary file, which is that red polygon that you saw in the animation. And we'll be looping over all of the geotiff files, which contain the raw data itself, and taking the zonal average over the region, excluding any no data values. For each of those spatial averages that we acquire, we'll be able to create a time series, one line for 2018, which is our control year, and one line for 2019, the flood year. Let's take a look at that plot. All right, here we go. Another thing that I've done to help with our visualization is that to make the plot a little less busy, I've only included data values over the specific region where plants were growing most vigorously during the growing season. The researchers found that the reduction in SIF, as you can see in the red line here for the flood year, represented about a 15% reduction in crop yields. And that's huge. It represents perhaps billions of dollars in agricultural losses. Doing some quick math, we can see that our 2018 peak, in this case, of 0.58 watts per meter squared steradian micrometers, around mid or early July of 2018, is about 13.7% higher than the similar peak of 0.51 or so in 2019. So even just using a roughly drawn polygon rather than the more rigorous approach of filtering by crop cover, we get a result that is fairly close to what we see in the study. On the other hand, the time series also shows that later rise in productivity later in the season. Whereas in 2018, we see a steady drop off towards the end of the growing season. This later peak in the 2019 flood year corresponds with the several weeks later planting date that farmers used to mitigate some of the effects of the flooding. As I mentioned before, if you perform this analysis again for some of the natural vegetation outside of the crop areas, you might see that some regions actually did better in 2019 because of the extra water stored in the soil. Nature can be resilient in ways that some agricultural systems aren't. So that covers the primary portion of our 2019 analysis, but I want to cover another case study of the 2012 drought, which occurred in the Corn Belt. And the motivation for that is apparent if you look at the yield plot for corn and soy in the United States. So let's turn over to that. And I touched on these graphs briefly during the presentation as well. So looking at our corn yield data, we can see that in 2019, while there was certainly a drop in yield that's noticeable, it's only about 5%. And one thing we can notice about that is that even though we saw a 15% drop in the peak SIF, that didn't result in a perfect 15% drop in yield in the crop. So the relationship is not quite that simple in this case. The motivation for looking at 2012, as I said, is that there's quite a conspicuous dip in yield in that year. And this was due to a lack of precipitation and extreme heat in 2012 over the US Midwest. If we look at the soy yield charts, we can also see that while 2019 saw a drop in yields, it's not quite as severe as the drop that we saw in 2012. Another thing that you may notice about this plot, if you're not familiar with agriculture, is that there's a consistent upward trend line. And this is due to changing agricultural practices and improvements in hybrids year over year that enable increasing yields. Because of that, when performing analysis of agricultural regions, it's important to choose control years that are consecutive years if possible, because of the increasing yield over time will also show up as increasing primary productivity and SIF over time. Let's go back to our notebook and change our analysis to look at the years 2012 and 2013. The reason why I won't be using the year before of 2011 is because that year also saw a moderate drought and a drop in productivity and yield. So I'll go back up to the beginning of section 3. And here we can see two variables, year A and year B. And instead of 2018 and 2019, I'll instead put in 2012 and 2013. And we'll use the same time range to cover the growing season. In different parts of the world, you may need to select different dates, or when studying different plots with different planting times, especially if the crop is a perennial or planted in a different season of the year. So now we can see that we're downloading the 2012 and 2013 growing season data. I find this example especially interesting in contrast to the 2019 case study because we're going to see SIF crash for a completely different reason. Essentially that there was no water instead of too much water. Let's run the animation cell again and take a look at what we can notice qualitatively about the data. In this case, the left side plot is going to be our anomalous year with 2013 as our control. As we can see, the SIF peak is quite low in the anomalous year compared with 2013. Even the unmanaged land in the Ozarks down here, like we mentioned in 2019, is relatively low in 2019 as compared with 2013. Although there was an early peak, there are patchy regions here suggesting that there was some difficulty in the growing region down here in the temperate forest. The amazing thing about GoSIF is that we can do this analysis and have confidence in what the data is telling us, even though both of these years were before the launch of OCO2 in the first place. You'll notice OCO2 launched in 2014, and both of these years are before that launch date. Lastly, let's examine the time series plot of these 2 years. So one thing I'll point out is that the labels will not render very well here since I've tuned it for the previous example, but you can hopefully still see what I'm talking about in this plot. Even though 2013 lagged somewhat in the early season compared with 2012, which could be for a variety of reasons, the big story we should see in this plot is just how muted the peak in SIF was in 2012. It was more like a plateau at levels that we would normally see in the early growing season. This much more dramatic crash in production resulted in a direct crash in yields, as we saw in the yield curve over here for corn and soy. I don't want to dive too deeply into the economics of this, but if you look at corn prices in that year, you'll notice that they also spiked, no doubt driven by the scarcity of new corn supply from that year's poor harvest. At any rate, I hope that these case studies have really illustrated the power of SIF data and how we can realize its full potential by leveraging gap-filling techniques. Whether it's through floods, droughts, heat waves, or even things like volcanic eruptions affecting sunlight, SIF can capture all of this information because it's measuring photosynthesis. Even though our analysis of these two case studies has been far from comprehensive, it should give you an overview of how gap-filled SIF data can be employed. If you want to take it a step further on your own, one homework challenge to consider is this, and this isn't an official homework. How would you validate the top-line gross primary productivity figures presented in the Yin et al. Paper abstract? Remember that there is a GoSIF GPP product that I mentioned earlier. So if we took that data, added spatially averaged GPP values, similar to the way that we spatially averaged the SIF values, for each time increment over the Corn Belt and over the growing season, we compared the sums of those values between 2018 and 2019, what might we notice about those sums? While the difference in the two sums probably won't line up exactly with the figures from the paper due to differences in the spatial aggregation technique, do you expect the percent difference should be comparable? Try this out on your own if you're curious and want to go even further with this exercise. So that concludes the code demonstration portion of this part, and thank you for your attention.
Thank you very much, Jackie, for that great presentation and demonstration. So now what we'll do is a summary of our session today of the salient points. And here's a summary of today's session. SIF is an excellent metric for assessing vegetation health and stress response. As we saw with the demonstration on the case studies of the impacts of floods and droughts. SIF can be measured from several satellite platforms, each with its own trade-offs. OCO and OCO3 provide high-quality SIF measurements, but they have limited spatial coverage and a relatively short observational record, up to 11 years. Gap filling or data fusion uses data-driven models to predict SIF values and extend spatial and temporal coverage. And GoSIF is a gap-filled product. So it's a gap-filled SIF product. It's a globally continuous SIF product with 0.05 degree spatial resolution. That's about a 6 kilometer spatial resolution. And an 8-day, monthly, and annual temporal resolution, extending back to the year 2000. And finally, floods and droughts cause vegetation stress, which reduces SIF. And here's a contact information for anyone that has more questions about the material that was presented today. You can reach out to Jackie Ryan or to Karen Ewan. And with that, we've reached the end of not only today's session, but this webinar series. I'd like to thank all of the participants and all of our invited experts. And we are now ready to start the question and answer session. The first question I want to use SIF data to analyze forest health and want to check, and I like to check it relative to air pollutants and their impacts on forests. I'd like to have some suggestions related to this.
Yes, the short answer is yes. So you can use SIF to analyze the forest health and check the impact of air pollutants on forest. So there are many studies that using SIF to assess the impact of climate anomalies on forest health, such as that what Jackie showed today is on cropland, but there's many studies using SIF to look at the impact of drought, heat stress on the forest. But you can also use the SIF to look at air pollutants. But the challenge is really to how to isolate the impact of air pollutants from other factors, so that such as heat and drought, because they could happen at the same time. In the document, I put the example of using SIF to investigate the impact of air pollutants on forest health, and I will put more references on this document. You can check it out later.
Wonderful. Thank you very much. The next question, number 2, I get this error. Does anybody know why? Permission error, access denied.
Yeah, so that was hopefully just due to having the folder open in Windows Explorer. I'm not sure if that fixed that particular user's problem. I will note that Windows is a bit less comprehensively tested than Mac OS. So if you are having an issue, I can look into it further.
Yes, please feel free to email Jackie, contact her directly if you continue having issues. The next question, number 3, I want to know the difference between the SAMs and target acquisition modes of OCO3. Can both modes be collected together for a site, for example, a flux tower site?
Yes, so these two modes cannot be collected at the same time, but they can be collected at different times, but over the same site. So basically, you can collect like today using SAM, but not today use target. And SAMS covers much broader area, so it collects observations over about 80 kilometer by 80 kilometer area within 2 minutes, where target mode covers a much smaller area, it's about 25 by 25 kilometers. So it's much smaller than SAM. And it's also primarily used for validation purposes. So not those target observation normally over TCON sites, which are surface remote sensing that are used for validation of the satellites.
Great. Let's move on then to the next question, number 4. SIF data has higher values in July, August of the year. What factors drive these values?
So as Jackie said in the training in the course, the SIF is a really indicator of plant productivity, while plants growth needs light, energy, and water. So these quantities are higher in July and August in the northern hemisphere. So that's the reason that a SIF has higher values in July and August in the northern hemisphere. In the southern hemisphere, is a different case. So in the southern hemisphere, it's the opposite. So SIF would have higher values in January, February of the year when you have the highest light availability and also the temperature is warmer.
Very good. Thank you.
There's a new question in the chat. What are the specific differences between NDVI and SIF values? I could try to answer that, or maybe Junjie, do you want to answer that?
Jackie, please give it a try. Yeah, please go ahead.
Okay, so as I mentioned in the presentation, NDVI is primarily a measure of the color of plants. It's created by taking a ratio of specific reflectance bands from, you can use a variety of sensors. It's kind of agnostic. SIF is a very carefully estimated measurement that comes from high resolution spectrometers. And it's more directly tied to the physiological response of the plant. Because of that, you get a much faster response of SIF rising and falling in response to changes in photosynthesis activity in the plant, as compared with NDVI, which is considered a lagging indicator. So, for instance, if you had a prolonged drought where plants stopped photosynthesizing, you might be able to observe that up to a week before you would see a similar fall off in NDVI.
Great. Thank you very much, Jackie. And Junji, if you'd like to add anything else, please feel free.
No, I think Jackie explained it really well. Excellent.
Wonderful. Thank you. Okay, so we have another question coming in. Are there plans to expand SIF coverage via additional satellites?
I can start.
Go ahead.
Jackie, you can add. So there is another satellite called Flex, which will be launched later of this year, on early next year. The Flex satellite will be launched by Italian space agency. That's just main observable is SIF. So that would increase observation coverage of SIF, and other satellites. I mean. May not have SIF as primary observables, but SIF could still be retrieved from those satellites, such as Temple, which our team members are working to retrieve SIF from Temple. Temple is a geostationary satellite over North America. If the team member could be successfully retrieve SIF from that satellite, that could be dramatically increasing the observation coverage of SIF over North America. So those are two satellites I know that could potentially increase the SIF observation coverage. Jackie, do you have anything to add?
I'll also note that improvements in gap filling is an area of active research. So there are many groups right now, including the ones that I mentioned in the presentation, that are trying to take the observational record that we do have and estimate SIF using other more highly available instruments. And actually, this was a focus of some research that I did earlier this year that is as yet unpublished, to take data from the GOES satellites, which are geostationary weather satellites operated by NOAA, and estimate SIF by training a model with OCO3 and the GOES data.
Great. Thank you both. All right. If you have additional questions as you go through the material, please feel free to get in touch with any of the instructors throughout this training series. Dr. Yunji Liu, Dr. Nick Parasu, Jackie, Karen, or any of the ARSET team members. So with that, then we've reached the end of this training series. I think it was a great training. I'm really excited to see so much interest in SIF and having a large community be interested in these sorts of data sets. So first of all, I'd like to thank all of the participants again for your interest, for your enthusiasm in this topic, and for all the great questions that have been coming in. I'd also, of course, I'd like to thank the ARSET team, Brock Blevins, Jonathan O'Brien, Sarah Cutshaw, Sue Monty, Selwyn Hudson-Odoi, Maria Marabito, Melanie Foyer-Cook, Natasha Johnson-Griffith, and others from the ARSET team that help put this together and make these trainings possible. And finally, I would like to thank the SIF team, who did an incredible job in putting all of this material and demonstrations together, especially for today's speaker, Jackie Ryan, who's been phenomenal in presenting not only the theoretical part, but also the very instructive demos. So I'd like to give the opportunity to Jackie for any final words before we close. Go ahead, Jackie.
Yeah, just thank you for attending and for your attention. And the last thing I'll mention is that we will be posting the homework, hopefully this week. The only required portion is the 11 multiple choice questions for receiving their certificate. However, I also wrote 3 optional exercises if you want to pursue any of the analysis that we did in these 3 code demonstrations further on your own. And those exercises focus on extending what we looked at to view different areas of the world, such as the sugar growing region in Sao Paulo region of Brazil. So yeah, thank you.
Super. Thank you, Jackie. And Dr. Liu, would you like to say any words before we close?
I just want to thank the whole team for putting this together. This is fantastic. And also thank for the participants from all around the world for your interest and for your active participation. And feel free to reach out to us if you have any questions when during our research, and good luck with everything. Thank you.
Thank you very much. And finally, Karen Yuen, who's been instrumental in really getting this training or making this training possible. So Karen, would you like to say any words before we close?
Thank you to all the participants for joining us for today and the whole series. And I do know that there is a survey that ARSET does provide. Please fill that out. This is how we are able to know what to put together and provide to all the participants, because your feedback, we really do look at that. And we work with great people like Jackie and Gingy to be able to put together these sessions for you. So we look forward to your feedback. Thank you again. We have a great team. And thank you to our ARSET team. Thank you to Gingy and Jackie. It's really an honor to work with you all.
Thank you very much, Karen. So yes, I just wanted to stress what Karen said, that there is a survey that will be sent out. We ask you to please fill out the survey. It is important to us and to the OCO mission, right, to understand what you're interested in, how you're finding the use of the data, what you would like to see in the future, what are some of the challenges that you're having. I mean, all of that is really, really helpful feedback for us and for ARSET and for the OCO team. So please fill out the survey. As mentioned, the homework will be posted on the training webpage today. The due date is November 12, I believe, and the certificate of completion will be provided to those participants that attended all 3 live sessions and complete the homework by the due date. So with that, I hope to see you all in the future again. We hope to have another SIF training sometime in the future, maybe the next step, something a little more building on what was presented this time around. So please let us know what you're interested in. Thanks, everyone, and wishing you all a great day.